so with apologies for the delay in the start, we will continue. So let me first recall a little bit what we did last time, which is the most important part. So what we saw is we had all these different R matrices. We had an R matrix, which I called R0L. The crossing of the auxiliary space with label 0 and some line L. Then we had an R matrix R0 prime L, which was the crossing of another auxiliary space, same line L. Then we also had an R matrix R0 0 prime, which crossed these two auxiliary spaces. Like that, 0 0 prime. And we gave all of them different weights. So this had 6 vertex weights, A, B, C. This one, A prime, B prime, C prime. And here we assumed that this had A prime, B double prime, and C double prime. It was also 6 vertex form with this 0 field assumption. So this here, we assumed that it obeys the ice rule and the 0 field assumption. Then it also has these 3 weights. And then we saw that we can equivalently parameterize this by rho and some spectral parameter u and this delta. Then we saw, well, this one has some rho prime, u prime, delta prime, and this rho double prime, u double prime, delta double prime. And we checked that, that this obeyed the Baxter equation, which graphically looks like follows. You have a space, auxiliary space 0 with a parameter u attached to it, an auxiliary space 0 prime and a parameter u prime. And we can draw this picture, crossing the line L. And this is equal to the same external labels, but then first crossing and then crossing this line L. And we saw that this is true if and only if all the deltas are equal and this parameter u double prime is the difference of u and u prime. This is called the difference property. In other words, in that case, if you like the formulas better still, the equation is R0 0 prime of u minus u prime, R0 L of u, R0 prime L of u prime is equal to the R0 prime L prime u prime R0 L u. So those two in the opposite order, and then this auxiliary R matrix moves through u minus u prime. And then moreover, we showed that if together with this, we moreover have that the R is generically invertible. And we showed that the function that sends the spectral parameter to any matrix entry of the transfer matrix, so some S prime P of U S, is smooth. We had entire effect. Then all of these things together implies that the transfer matrix is complete, corresponding to the rho auxiliary space 0 and 0 prime. So that's what we should do. And just to actually say a tiny little bit more about this last little bit, the generic invertibility. In fact, we can note, it's easy to check this, that we have the following relation: R of u times R of minus u is A of u, so one of the entries, A of minus u times the identity. Which graphically means that if we have this, we have a double crossing of lines, and we can just straighten them out, maybe up to a constant that depends on the normalization, so it's proportional. And also, finally, you can think of this. So this is sometimes called unitarity, this condition. And we also have the property, this is the last property, which is often very useful, that the R matrix at 0 is some constant, A of 0, times the permutation. So graphically, it said that if you have an R matrix with U and Q, then we can open up these lines like this. And this is then sometimes called the initial condition. It's kind of like a normalization condition. So this is just a tiny little bit to add. So then we have all the properties of the R matrix, namely the Young-Baxter equation, this unitarity, and the initial condition. We have it on one blackboard. And last time, we used this last property was useful to actually compute, to get the shift operator and the exact homotonic out of the transfer matrix.
Constant doesn't have to be 1.
No, right. So last time, remember, I chose my row to be 1 over A, essentially. I mean, I chose my row so that 2 set A equals 1. So last time we didn't see these constants, but they can be there. It's not important. It's just a normalization convention. In some normalizations, in fact, you should take the residue at 0. So that's a simple pull, and instead you fix the residue to be the permutation. Maybe you have 2 constants. Okay, then in my numbering, we're now up to section 5.4, Young-Baxter algebra. So remember, we had our partition function. We first sliced it into horizontal pieces, then we sliced it into vertical pieces, which were the R matrices, and we showed that this, like here said, the Young-Baxter equation for the R matrix with some simple arguments showed that the transfer matrix is commuted under a few extra assumptions. So what we will actually look at today is an intermediate object, which was already there last time secretly, and it's called the monodroom matrix. I'll denote it by T0, because remember, I suppress the subscripts 1 to L of U. And graphically, it is just, I'll now introduce this shorthand. It's this, which just means it's a horizontal row of the lattice, but without periodic boundary conditions imposed. Like that. And since we will use it a fair bit, I will just abbreviate all the vertical lines by this triple line with a big arrow on top. And by now, it should not be a surprise that we will view this as a matrix from our auxiliary space, so that copy of C2, and the Hilbert space of the spin chain to the auxiliary space. Remember, we always put the horizontal first and then the vertical to the Hilbert space. So from this picture, we read off that the formula equals R0L of U all the way down to R01 of U. We can also write down its matrix entries. If you fix an auxiliary, so R prime and then S prime vector P0 U R S vector, and this corresponds to the picture where we have 0 U R, where R is now a fixed spin. At the bottom we have our space is 1 up to L with fixed spin S, outgoing horizontally R prime, and on the top. So that picture is it has fixed spins on all the outer sides, so you can use the summation rule for internal edges to compute something, and that's the matrix entry of this monodroom matrix. And we note that we always think of auxiliary space, Hilbert space, auxiliary space, Hilbert space, like I wrote here. So what is this thing good for? Well, from the spin chain point of view, it contains 4 what are sometimes called quantum operators because they act on the Hilbert space of the quantum mechanical model that the spin chain, which are operators on the Hilbert space itself. Namely, I can think of this monodromy matrix as a 2x2 matrix in the auxiliary space with entries that are operators on the Hilbert space. So in my graphical notation, let me draw the matrix with all the entries carefully. So the incoming line horizontally, first we have dotted, and then we have stuff, and then we have thick, and then we have stuff, and here the outgoing line, dotted, and the outgoing line is thick. This is with respect to the fixed spins on the external edges that are auxiliary. So then the internal picture is the following. We have either this picture, or we have this picture, or we have this picture, or we have the one which has fat lines incoming and outgoing in the auxiliary direction. And of course, they should have all the labels. And this is a 2x2 matrix in the auxiliary space. I'll give it a subscript 0 by our convention. And then these entries, they're usually called A of U, capital B of U, C of U, and D of U. Those are these quantum operators, A, B, C, D. They act on the same space as the spin chain. In other words, this is a 2x2 matrix on auxiliary space with entries that are operators on the Hilbert space of the spin chain. And these entries are usually called the A operator, the B operator. Now, why is this a useful object? And why did we already see it last time? Last time we only really cared about this transfer matrix, which graphically is this. But by our summation convention for the periodic boundary conditions, we have it's equal to this plus fat lines horizontally. In other words, it's a trace over the auxiliary space of the monodromy matrix, which is also equal to the A operator plus the B operator. So these A, B, C, D, they in particular contain the transfer matrix, or they generate the transfer matrix. The last time we saw, well, this statement here, that the Baxter equation plus some extra conditions imply commuting transfer matrices. Today we actually have a simpler claim, which we already proved last time, really. So let's us suppose there exists what I call the auxiliary R matrix, so just the R matrix that's rotated a little bit. Now we know that it has 2 parameters, U and U prime. And denote it like this. As before, and assume that it obeys the Young-Baxter equation. Given this data there, so given an R matrix, given a pair of R matrices, assume that there is such a R0, 0 prime. Then we have what are called the RTT relations. Namely, R0, 0 prime of U minus U prime, C0 of U, C0 prime of U prime, which pictorially means that we have U0, 0 prime. We have, this picture. So it looks like the Young-Baxter equation, but now the vertical line is replaced by a stacked triple line. And the claim is that we can move the R matrix through to the other side. And then we get the same external kind of things. Now that that line is on the right of the crossing, like this. So in formulas, this, now we see that the last one to act is the T0 prime of U prime. then the 0 of u, and then the r 0, 0 prime of u minus u prime. So the proof is just this train argument from last time. It's very easy. We already showed this last time, actually. And last time we also took into account horizontal boundary, the periodic boundary conditions and the invertibility of the R matrix, but now we don't actually need this. We just have these relations, and what they say is that T of u and T of u prime commute up to conjugation basically by this R matrix, if the R matrix were invertible. And more precisely, they're intertwined by this R matrix like that. So the R0, 0 prime brings you from one auxiliary space to the other. And then it doesn't matter in which, it flips the order of the monodromy matrices on the two auxiliary spaces. Okay, so let's see what this really means. I hope that the proof is right here, right? You just expand the picture, you use this many times, and that's let's get it. So what this contains, okay, so that's the proof. So this encodes, well, it's a relation on two auxiliary spaces. So we have a four-dimensional space. So it encodes 4 by 4, 16 different relations between our A, B, C, and D operators with coefficients that come from the R matrices. So with structure constants, let's say, which are equal to entries of the R matrix, of this auxiliary R matrix. So, for example, by the way, here I use my conventions, right? That this transfer matrix acts as the identity on the second auxiliary space, this transfer matrix acts by the identity on the first auxiliary space, which is why I only have the subscript 0 or 0 prime. And then, as always, I omit the subscripts for 1 dot 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 L. So you can think of this as a 2 by 2 matrix, but you can now think of it as being embedded in as a 4 by 4 matrix. This is another 4 by 4 matrix, or alternatively, this is the tensor product of two of these R matrices in auxiliary space. And so, if you want to just multiply matrices and so on, then the following corresponds to the 1,4 entry on the C2 for operator on the two copies of the auxiliary space. But of course, we will just do it graphically. So let's draw this picture again, and then we fix some boundary conditions in the auxiliary space. So we have our 0 u and 0 prime u prime. Let's first just draw the same picture. So we have this is equal to this, 1 dot dot L, and that should be the same as first crossing. And then our pair of monodromy matrices, now acting in the opposite order. So now the boundary conditions that I first want to fix is, let's take thick incoming lines here and thin outgoing lines. So dotted outgoing lines, like that. But this is a way to take an entry in the tensor product of two auxiliary spaces. We fix the spins on just auxiliary space. Well, these here are R matrices, and they obey the ICE rule. And we know from the ICE rule that if we have two outgoing dotted lines, then by our path conservation or spin Z conservation, we know, so let me do this in a different color, let's say in blue, these lines must also be dotted. And similarly, here, if we have two thick incoming lines, then the outgoing lines will also be two thick lines. So this is because of the ice rule. Yeah.
Your convention of this basis, is it the 1-4 entry or the 4-1 entry?
Maybe it's a 4-1 actually. Might be right. So well, this is the 1-1 entry, and this is the 1-2 entry. Right? I mean, you would call this 1-1, 1-2. So it's the 1-4 entry. All right, so we can read off what this actually is. Maybe. Here we have, if I'm very careful, it was our A plus, but it's just A of u minus u prime. And then we have a B operator, which is our B of u. And then we have another B operator of u prime. This is what we get on the left-hand side. Whereas on the right-hand side, we get B of u prime and B of u. And then our A, which is really an A minus, if I'm very careful, of u prime. Now, of course, in our case, A plus and A minus are the same. This is our zero field assumption. So what we see is that the B operators with two different spectral parameters, they commute, provided A of u minus u prime is non-zero. So this is some sort of genericity condition similar to the invertibility of the R matrix that we needed for the commutativity of the transfer matrices. In fact, the determinant contains some factors of A. But so let's say almost always B operators commute. So this is one of the relations of the Young-Baxter algebra. A little exercise. Likewise, check that in fact A operators commute and C operators commute and the D operators also commute. Let's say almost everywhere, almost always. Okay, so we have these four operators, and if I just take one of them, then I still have a one-parameter family of operators, and this is a commuting family of operators, a bit like our transfer matrix was. But there are many more relations, so let's have a look at another type of relation. So another example, which would correspond to the 1,3 entry. So again, I'll first draw my picture. Let me not, well, okay, I guess I should. So we have our picture, which looks like this. Triple line going through, equal to first crossing, then triple line. And now I want to take the first incoming horizontal peak and the second incoming pin, and I want to just take pin outgoing. So here the same, peak, and thin, and thin, and thin. So again, we can use the ice rule to see that on this side, the dotted line is going to propagate through the vertex. On this side, we directly have, if I'm very careful, A plus of u minus u prime. Then we have a B operator of u, and now we have an A operator of u prime. But on the other side, there are now two possibilities for our vertex. Let me just draw them. So we have the same picture. I will not write all the labels anymore. So we have this, or the same, but with different ways that the lines propagate. So we have our external boundary conditions: tick incoming, dotted outgoing, tick incoming, dotted incoming, dotted outgoing. And now this vertex, it can either go straight, that's the path, or it can turn. these are the only two possibilities which have non-zero vertex weights. So I use like my summation convention from the internal lines, and I use that the R matrix, well, obeys the Ith rule. So the number of incoming paths have to be equal to the outgoing paths. So what do I have here on the right-hand side? Well, this here is a B vertex. To be precise, it's a B minus of U minus U prime. Let me just write it in front because it's just a constant function, so it commutes with all the operators. Then I have an A operator of U prime, and then a B operator of U. Or I have the C minus vertex, U minus U prime, and then B of U prime, A of U. So let's clean up our notation a tiny little bit. So let me replace U by V and U prime by U. Then the relation that I found is that A of U, B of V is equal to A of V minus U over B of V minus U. Then the B of V A of U minus C B minus U over B B minus U, and then we have the B of U A of V, and this is almost always, let's say, right, provided I'm allowed to divide by this B. So what does this relation say? Well, it says that if we have an A operator, we can commute it through the B operator, like here, and we could just get some simple coefficients, which are structure constant, if you wish, of the algebra. But in the process, it's also possible that the two swap parameters. So A always moves through B, but in one case it keeps its parameter, and in the other case it swaps the parameters. So this will be an important relation, which I should try to remember to keep. We will use it. Now, an exercise is likewise show or check that we also have the following relation. If we now wanted to move a D through a B, then let me abbreviate such ratios by just A over B of some argument. So now it's not V minus U, but U minus V. And this is the term where the D just moves through the B. And then we have C over B again with U minus V. And then they move through each other but swap arguments in the system. That's another relation. And so in fact, here we already have four relations between the ABCD operators. So we were missing 12. Here there are 2 of them. So basically for each pair A and B, or each pair of quantum operators, there's a relation that tells you that you can move one through the other, but you will generate 2 terms in the process. So there's one for moving A through B and generating 2 terms. There's one for moving a B through an A and generating 2 terms, and so on. And this accounts for all the remaining 12 relations that we were going to find. So you can repeat this process and find all the other relations if you want. But we will not need them so much. However, it's good. I should have the following exercise to check that everything is consistent. So find the commutation relation for B and C. For A and B. So A of U and D of V, let's say. And as a kind of a partial hint, let me mention that in this relation, B and C will appear. But you don't need to bother worrying too much about that. And you can use this to check, to recheck, as we already did it before, that the transfer matrix is commute. C of U and D of V is 0. So you'll need a term You'll need a term for moving A through D. You'll need a term for moving D through A. You'll generate some extra stuff. but you can check that all the relations together guarantee that the transfer matrices commute now from these RTT relations.
When you're moving A through B or when you're moving B through A, it's the same operators that appear in both relations. Are they the same relations or they?
No, they're a bit different because you see here we think of it as A, so A starts on the left, and so here there's only one A on the left and one term with A on the left and two terms with A on the right. So there's another relation which has the opposite, which has two A's on the left and one A on the right. So that's more like we interpret it as a relation for moving B through A.
And can you combine them and simplify them?
Of course, they're just different relations. Of course, they're all compatible, so you can kind of check that anything you can do will work. I mean, will be consistent, but they look a little bit different. So it really depends on whether you would want. It's not a commutative algebra, so moving one operator to the other, it just gives some stuff. Okay, and this is one of the other relations which we will use. Okay, so let me remove this stuff. Maybe keep this in case. Now, all right. So what is this Young-Baxter algebra really? Well, it is an algebra with generators A of u, B of u, C of u, and D of u, and relations contained in the RTT relations. And what you can check is that this is in fact associative. So all these rules are compatible because of the Young-Baxter equation. So now if we take the RTT, they just tell you what the relations are for two generators at a time. But now we can consider products of three out of ABCD. So for instance, ABB or ABC or whatever, and we can start moving stuff through each other. And the fact that all of these possible ways of computing the result are consistent follows for the Young-Baxter equation now for the R matrices in the auxiliary space.
At different points or the same? At
So
different...
you would have many different values of the parameters. Yes, right. So A of U, B of V, C of D, or C of the W, whatever, something like this. And so that is what the Young-Baxter algebra is. And let me give some examples. So I will not. So this is really where all the stuff with quantum groups really is kind of hiding. So for example, let me do it here. So we've seen some different R matrices. So we had our X, Y, Z spin chain, which appears here and there a little bit. Then we had our X, X, Z spin chain, which is less general, and then leave, let's say, two lines open, X, X, X spin chain. So then here we had our 8-vertex R matrix. Here we had our 6-vertex R matrix. And here we had what is called the rational 6-vertex R matrix, which let me just give it explicitly. R of U was U plus the permutation, where U is the multiple of the identity. So I can take these different R matrices. It will give different structure constants. They obey our Young-Baxter equation and other things that we need. So it gives different Young-Baxter algebras. For each of these different R matrices, define a different Young-Baxter algebra. In this case, the Young-Baxter algebra, well, it has another name. In this case, it's called the Sklianin algebra. For X, Y, Z. In the case that we are studying mostly, it is the U, Q of L, G, L2. But this is called the quantum loop algebra. Which is also the same, that's our second line, sometimes it's denoted as UQ prime of GL2 hat with C is 0, which is an example of a quantum affine algebra. And for a quantum affine algebra, it by itself it has a central charge. Here it is 0. That's what this C is 0 means. So only level 0 case. And then it has a derivation, a degree operator. And the prime means that we don't get it from the monodromy matrix. So these two are different ways to think about the same object. And both of them, in technical terms, we should say that this is in the principal grading. Not important. But with the precise R matrix that we take, this is the principal grading. You can modify your R matrix a tiny little bit to make it relate to the Hecke algebra and things like this, and then instead you get this in the homogeneous grading. Finally, for the XXX spin chain, this is the Youngian of GL2. So all of these are infinite dimensional quantum groups. So they have some coproduct and antipodes and so on.
I don't know. Kind of, I don't know. Where is the camera? This is camera. Yeah.
Right, so we're almost back. Very good. Right.
Yeah.
So we have these different R matrices, which give different versions, examples of Young-Baxter algebras, and they're called the Slianen algebra, which is complicated, quantum loop or quantum affine algebras, which are much less complicated, and the Youngian as a special case. They're all infinite dimensional quantum groups. And to be precise, this is called the Fadeev, Reshetikhin, Takhtajan presentation. So all these quantum groups have various different presentations, and this presentation by IPHT is called the FRT presentation. And of course here, in our case, what we're really doing is we have a representation of this quantum group because we really act on our Hilbert space. So our monodromy matrix ABCD, they're actual operators rather than just formal kind of abstract operators. So it's a representation of such a Young-Baxter algebra on our spin chain Hilbert space. And maybe a remark related to the question about how should you really interpret this dependence on all these parameters. Let me just write this down. So really, how you should properly define all of this is you should view it as formal power series in the spectral parameter U or U inverse. So for instance, we can normalize the R matrix to define R bar of U, which is R of U divided by A of U. So we set the 1,1 entry to 1, like we did last time. In other words, we choose rho so that A is 1. And then you expand the A operator as some formal power series, K positive, let's say, of AK, and then U to the minus K, etc. And what one needs to demand is that the zero mode of A and the zero mode of D are the identity, whereas the zero mode of B and C are absent. I guess it depends a little bit on the representation. Maybe it's a multiple of the identity. But So that is the proper way to really interpret all these different operators with different spectral parameters. So if you have a relation between operators with two parameters, you expand everything into modes, and then you collect coefficients, and then you will get lots of commutation relations for all the different coefficients, and those are really properly thought of, the defining relations in this FRT presentation of all these Young-Baxter algebras. But it's really much more convenient than doing this proper expansion as power series to just think of it as being generated by ABCD, which is what we will do. But so that's really the meaning, how you do this. If you have like triple all the products of three operators, and you have formal power series in three different parameters, so you expand on everything and you collect modes, coefficients, and those are really the relations. Yeah.
So you meant, you said representations or you meant basic representation.
Yeah, I guess it, yeah. Are they? Well, I mean, depending on your length. So if your length is 1, then probably it's not faithful. So, no, they're just the physically meaningful. I mean, the representations for spin chains that are relevant, and also for these vertex models. But I am not making any claim of whether they're faithful or not. I don't know. Probably if the length is sufficiently big, but I can sure what. Okay, so that's this Young-Baxter algebra, and that's really where the quantum groups and all this kind of stuff that we use a lot in integrability are hiding. But besides this example/remark, I will go back to a much more naive level and just work with these operators and use them to really analyze our spin chain. So that's the next goal. Maybe I can write it here. Let me just do this. So then we go to the part that I promised long ago, which is the algebraic beta ansatz. Abbreviated to ABA. So the goal now is to reconstruct the beta ansatz, namely to find the eigenvectors of the transfer matrix D of U. So it's Wiener wall. So let me just remind you that because the transfer matrix preserves the spin in the z direction, the number of thick lines or the number of dotted lines, we are allowed to do so per fixed m, which was the number of downspins. So so per m, which was equal to L over 2 minus sz, which was equal to the number of our downspins. So here I still have my ABCD operators drawn. So from the graphical notation, it's clear. So graphical, it's clear. Well, we see here that the A operator, it kind of inserts a dotted line and then it extracts the dotted line. So by the ith rule, it preserves the number of paths that go from the bottom to the top. So it's clear that the A operator and the D operator, likewise, preserve M, whereas the B operator injects a path or downspin. In other words, it sends us from M to M plus 1. And conversely, the C operator extracts a downspin, so it sends us from M to M minus 1. So from this, we see that the B operator is a natural candidate for a creation operator because it creates one downspin. And that's the goal. So we will do kind of like a Fox space type of construction of the, that's what the algebraic beta ansatz is. It's like a Fox space construction of the beta ansatz. So the B operator is a natural candidate for creation operator. So let's start like before at our M is 0, which is called the pseudo vacuum, because it doesn't need to be the actual ground state of the spin chain. It depends on whether you take which sign you took or what the value of delta was. So it's not always the real ground state, but it acts as the ground state for our Fox space construction, pseudo vacuum, and I will call it the vector omega, capital omega, which is just a vector which has all spins up. And it obeys the highest weight condition. That the C operator acting on omega is 0. Right? We start with a vector which has no spins down, and then we want to extract the spin down. Well, it's impossible, so the result is 0. So this is kind of the analog of a highest weight condition in this setting. Since A and B preserve the number of downspins, it's certainly going to be an eigenvector for them. So the only thing we just need to do is compute the eigenvalue of the transfer matrix on this thing. So let's do it. So we compute, well, the D operator acting, or let's say the A operator acting on omega will send it to a multiple of omega. So let's compute this matrix element, which graphically means that we have dotted lines on all sides, like this. But of course, by the ith rule, the internal lines have to be dotted as well. And then we read off that this is just a product of A vertices, so it's A of u to the power L. Likewise, if we compute the same matrix elements of the D operator, which gives the action of the D operator on our pseudo vacuum, then now we have thick horizontal lines with dotted vertical lines like this. By the ith rule, the internal line must now be a thick line because it has to go somewhere. So the only thing it can do is go straight. This is B to the u, B of u to the power L. And let me call this alpha of u and this delta of u, the eigenvalues of the A operator and the D operator on the pseudo vacuum. Let me call it alpha and delta. So then from this we see that the transfer matrix acting on omega gives the eigenvalue lambda of u on omega, where the lambda of u is alpha of u plus delta of u. To be precise, actually, this condition here, being killed by the C operator, is kind of like the analog of being highest, and then this is the analog of being a weight vector in general. So the eigenvalues of the A and the D operator, they play like the role of the weight of the vector in terms of representation. So together, this is really the precise highest weight condition for this Young-Box algebra representation. Okay, so very good. So a bit boring though, but good that the pseudo vacuum itself works. So now let's go to a bit more interesting example. So let's do one downspin. So we consider this vector which we get by acting with the B operator on this vector omega. So the entries of this, for the coefficients, well, the entries of this is a vector. So the entries are graphically, so remember my notation for the coordinate basis, right? This meant downspin at site L. So we know we start with 0 downspins, we inject 1 downspin, so it can end up in principle anywhere. So let's find the corresponding coefficients. So graphically, what we do is we inject the downspin, then we have some stuff happening, then we extract the dotted line. We start with all dotted lines, and then at some point we get a thick line going up like this. By our summation convention over internal lines, we sum over all of them, but the only non-zero possibility is when the thick line goes straight and then turns at side L, and then we get the dotted path. So let's read off the corresponding weight. Well, we have L minus 1B vertices. So we have B of U to the little L minus 1. Those are the straight lines on the left. Then we get a C vertex, which is where the line turns. And then the rest is A vertices. So we have big L minus small l, many A vertices. So that's the weight that we read off from this picture. And if you like to emphasize vertices, then this is B minus C minus A plus. So let me rewrite this a tiny bit. It is the C of U over the B of U, A of U to the power capital L, and then the ratio B over A of U. Sorry, it was V, that parameter. I'm just replacing all the U's by the V's. B of V over A of V to the power little l. Now we recall from our coordinate data ansatz that for M is 1, the wave functions, these coefficients, they should be plane waves. Right? So we should be able to compare this with plane waves. So we know that this should be proportional to e to the I p l. In other words, we need that b over a of g should be e to the I p. Now we remember what our b over a was. So let me write it explicitly. This was the sinh of v divided by the sinh of v plus eta. So at this point, it's traditional to change your parameters a tiny little bit and introduce something called the rapidity, which we call lambda. And we define it to be precise, minus I times v plus eta over 2. You see this v plus eta over 2 is kind of natural because then this ratio becomes a little bit more symmetric. We get a shift in one direction and a shift in the other direction. And the I is just kind of conventional. So what we now get is that the sin, the normal sign, because of the I, of lambda plus I eta over 2 divided by the sine of lambda minus I eta over 2 should be equal to e to the IP. A reason why these rapidities are very nice is the following little exercise, which needs a little bit more space to write probably. So remember that we had our scattering matrix E of P, P prime, let's say. It was minus 1, minus 2 delta E to the I P plus E to the I P plus P prime divided by the same with P and P prime swapped. 1 minus 2 delta e to the I p prime plus the same exponent e to the I p plus p prime. So the exercise, so this was the definition. The exercise is to check with the exclamation mark for the important point, that this is now equal to the sine lambda minus lambda prime plus I eta sine lambda minus lambda prime minus I eta. So we see that these rapidities are very nice because the scattering matrix, which depended on two variables, only depends on the difference of the corresponding rapidities. Where here, of course, I assume that eta p is defined by lambda like this, and likewise p prime in terms of lambda prime. So this is a kind of a difference property. And in fact, these rapidities were introduced very long ago by Orbach already in the 50s, I think, or so. So by these type of motivation. Let me erase some stuff. Red. Orange. So we continue. So okay. So the point is, we see that this is certainly possible. There was some function of p we can now identify with v. And just to emphasize kind of what this means is that, so in particular about these rapidities, if we take the Heisenberg xxx limit, so remember that what we did is we took the limit for eta going to 0 of the R matrix, but with u rescaled by eta, and then divided by eta. Or we chose our this is this R matrix that I wrote down before, is u plus the permutation. So what this means is that our rational coefficient A of u is just u plus 1. Our B coefficient rational limit is just u. And the C coefficient in the rational limit is just 1. So in this particular case, we get that the rational rapidity as a function of the quasi-momentum, which is defined as minus IV plus a half now, is just a half times the cotangent of p over 2. So in this rational limit, we can really explicitly invert this relation here if we take the limit correctly of the left-hand side. And in the trigonometric case, you can also do it, but it's a little bit more complicated. You get some arctang of some ratio and blah, blah, blah. So it's a bit more complicated function, but it can still be done. Okay. Let me take a few more minutes to just finish the M is 1 case. So the upshot is, so now what we do is we define, let me call it the beta vector, so the vector b, depending on the parameter b, which is this b operator acting on omega. This is the vector. So we just kind of showed that it's a reasonable candidate at the very least for our transfer matrix eigenvector. It contains the same kind of degree of freedom as the plane wave did. That's the right number of downspins. So now we're going to check whether this is really an eigenvector for transfer matrix. P of u eigenvector. So we need to compute this. Well, we want to evaluate the action of the transfer matrix on this vector. So we do it separately for the A operator and for the D operator. And so what we will do is we will use the Young-Baxter algebra relations, so these R2T relations, and the eigenvalues of A and D on omega itself. right? So what we will want to do is we want to compute, for instance, A of U, B of V on omega. And we can do this if we can first move A through B, for which we have a commutation rule, and then we know how A acts on omega. So that's what we will do. So let's just do it. Here we have our top orange relation over there. So we see that we're going to get A over B V minus U. Then we get a B of V. Then we have A on omega, which is just alpha of U on omega. And then we have minus relation C over B of V minus U. Then we have a B of U. Now A on omega, so now we get alpha, but now on V because they swapped parameters. So alpha of V omega. In other words, what we get is alpha of U, A over B, V minus U, and then the beta vector with parameter V, minus alpha of V, C over B of V minus U, and then the beta vector of U. And this was the action of the A operator on U on the beta vector with parameter V. Now, a little exercise is that likewise, okay, it's so easy that I don't even know. Well, do likewise for the D operator on the beta vector with parameter V. And the result, if we put everything together, is that the transfer matrix of U acts on the beta vector with parameter B to be eigenvalue depending on U and now also on V of beta vector with parameter V plus some coefficient which I will call psi of U comma V and then the beta vector with parameter U instead. And this lambda of U V is U to the is alpha of U A over B of V minus U plus delta of U A over B U minus V and psi of U comma V is alpha of V C over B. Well, sorry, there should be a minus alpha of U C B V minus U plus also minus delta, excuse me, alpha of V minus delta of V C over B and now U V. Recall in our parameterization that C was a constant, so it's an even function if you wish, and B is an odd function, it's just a sinh. So what I can do is I can actually factor out this coefficient. I can write that this is C over B of U minus V, parentheses, alpha of V minus delta of V. So from this we see that this beta vector with parameter V is an eigenvector with eigenvalue lambda here, provided this psi coefficient vanishes. In other words, we have a wanted term and an unwanted term, and the unwanted term should vanish. So this psi should be equal to 0. And this last one is true precisely when 1, so I'll rewrite this a tiny little bit, is equal to delta over alpha v. But now we recall that delta over alpha is just b over a of v to the power L. And then we recall that we've identified the ratio of b over a of v as the quasi-momentum. So this is e to the IPL. So we see that the cancellation of the unwanted term, coefficient of the unwanted term, gives us back the momentum quantization, so the beta ansatz equation for m equals 1 here. And provided this is true, our beta vector is a correct vector with some known eigenvalue. So this here is our m equals 1 beta ansatz equation. So the upshot is that we have a natural creation operator, and indeed it provides eigenvectors of the transfer matrix, provided unwanted terms that are generated by this commutation relation where the two swap parameters vanish. And at least for m is 1, this cancellation of the coefficient is precisely our beta ansatz equation. So I think this is a good point for the break, and then after the break we will extend this to general m and do some other things. Are there any questions? So last little bit, we're going to really do the algebraic beta ansatz. I repeated everything on the left that we found so far. Reference. So now, the claim of the algebraic beta ansatz, so the important result is the following: that the vector v with the underscore b, which is b v1 all the way up to b vm on omega, obeys similar equation to what we found before. So the transfer matrix acts on this algebraic beta ansatz vector by some lambda depending on u and all the parameters v on this beta vector plus a sum from little m going from 1 up to big M of psi m u v, and then the beta vector where we replace the mth parameter by u. So these would be called the wanted terms, because that means that v would be an eigenvector and these are unwanted. So it's really just a generalization of what we found before. By the way, I just chose psi because I thought it's like the ugliest letter that I could think of. So it's the thing that we definitely want to stick to 0. Okay, so the proof goes as follows, and I think this is really, really nice. So what we want to study is the product A of u and then B u, B1 up to Bm. So let's first do this without acting yet on the 0 vector. So I claim that this is the following form. It is some coefficient n of A, depending on u and v, and then we have lots of b's again, and A has just moved through. But this will be true, sorry, with some coefficient na. And then we get lots of other crap. So at each step, the A operator can either keep its parameter or it can swap the parameter. So the A operator can end up with any of the parameters, and there are many terms that contribute to the same things, but the result can always be written as a sum from little m is 1 to big M of na sub m of u v, and now we have b of v1. At some point we get b of u, and then we have b of vm, and then finally a of u, of v little m, like that. So let's try to find some of these coefficients. So easy is to find this first coefficient. UV. So we'll look at our relation, which I'll line in orange on here. So recall, A either passes through B with some simple coefficient or it exchanges parameters. So the only way for A to ever end up in the end keeping its parameter is if you always pick up the first term here. So this coefficient is just the product of what you have there. So it's the product over m is little m from 1 to big M, and then the ratio A over B of V little m minus U. Out of all the 2 to the big M many terms that you generate, this is the only one that contributes to the coefficient where A keeps its parameter. Now another easy coefficient is the one where the A ends up with V1 only. So if A ended up with V1, so the coefficient NA1 UV, the only way for this to happen is if N exchanges the parameter with the first B and then keeps its parameter forever. So this coefficient is just minus C over B of V1 minus U, corresponding to swapping parameter with the first B, and then we pick up, so we have a product from little m is 2 up to big M, A over B, but now its parameter, so we have V little m minus V1, which is the new parameter of A. So this one is also very easy to find. But of course, if you now get want to compute n subscript 2, then there will be two ways to end up with V1. You can either exchange or not the parameter here, but you have to exchange again the parameter in the second step. And it gets worse and worse and worse. So there will be more and more and more coefficients to contribute. However, there's an extremely nice trick. Remember, we have our other relation that says that these B operators commute. Now, B operators, the B's commute. So what this means is that the left-hand side of this equation up here is the same as when I would swap V1 and some V little m. Because the B's commute, so I can just rearrange them in any order that I want. But of course, by consistency, on the right-hand side, we see, well, firstly, we see that our NA, so the coefficients where A kept its parameter, this is nicely symmetric under this swap. So like that. So that's fine. However, if we now compare on the left-hand side AM, which is the one that we want to find, then we see that this is equal to the NA1, which we just computed, with those parameters swapped. Because that's, you see here, the coefficients of the B by A. So we just do this operation on what we found there, and we see that this is minus C over B, V M minus U, product from M, let's say little n is not equal to M, up to big M, A over B, and then we have V N minus V M. Like that. So by the way, to be honest, this proof is an almost proof. What I use here is I use the assumption that all these products on the right-hand side are independent, because then I can compare coefficients of those products. To do this really properly, what you can do instead is prove by induction. So one proof is by induction, and it's rigorous. But first we need to know what to prove. And this argument that I'm giving you now is kind of a heuristics, which nicely determines everything, and then you'd use induction to really do the proof, and not rely on this independence of all the different terms in there. So likewise, exercise, okay, a similar relation for the D operator. So what we see, if we combine everything, so the result is that our lambda of u and v is alpha of u times na u v plus delta of u, and then our coefficient with d operator, depending on u and v. And all these coefficients of the unwanted terms are alpha um, na m u v plus delta m and d subscript little m u v. And let me write this a little bit more. So I will, this means that it continues here. So using the same trick as before, we use that the c is constant, so even, the b is odd. So I can extract again the c over b of u minus vm. And then I get some term which I will call beta-ansatz equation, BAE subscript m, depending on u and all these. And then this will be divided by, so times the product over all the n which are not equal to m, up to big M, of b, v, n minus v, m, minus 1. So that's some denominator that I get from these coefficients. And here, what I denoted by BAE sub m of u and v are, well, let me write out what we found so far. A vm power L, product over little n not equal to little m to m. Then we have a to the v n minus vm. And then we have minus 1 to the m. This minus 1 to the m comes from the fact that these b, so look at the coefficients. We see that these b's here, they have the opposite argument, and the b's are odd. So I can reverse the argument to extract this whole denominator here, but in one case it will give sign. That's where this name comes from. Then we have b, v, m to the L. Then similar product n not equal to m up to m again, and then a with swapped arguments, v m minus v n. So we see that this vanishes if and only if, up to genericity kind of conditions, like before. We have a over b of vm to the power L is equal to minus 1 to the m minus 1 product m not equal to m, and then here we have a of v little m minus little n divided by a with the reverse order, like that. And these are beta-ansatz equations. So if you really now that we know what we want to prove, you use induction to really prove everything rigorously, then we are done with this proof. And there's a little exercise here, which is important, of course, that we should check that this matches our beta-ansatz equations from some lectures ago, so section 3 and 4, and it matches the transfer matrix eigenvalue, which back then depended on quasi-momenta, from section 4. So you see that this computation is really simple. It uses just 3 relations out of all these RTT and Wechsler algebra relations. It uses some simple symmetry arguments to determine all the complicated coefficients from the simple ones, which you can just read off. By the way, the fact that this works is of course due to basically the Yang-Wechsler equation for the entries of the R matrix. So those functional equations are the ones that underlie all these combinations, these kind of resummations of all the complicated coefficients to give simple factorized forms. And then we find these transfer matrix eigenvalues and beta equations and then corresponding beta eigenvectors, all by much simpler computations. So here the computation for general n is actually faster than what we did for the coordinate beta ansatz just for m is 2. So you see that this is really, really extremely powerful. And the reason is that we have this
One thing which is not good is you don't get the eigenvectors.
Well, right. So the B operators, I mean, these beta vectors, they look more complicated, more implicit. In terms of linear algebra, so if you would want to put it in your computer, it's very good because you can just act with B operators. You still need to solve the beta equations, but that was true in any case. One thing that indeed is not so obvious is that if you now take a wave function of this, so you compute entries, that it actually matches the beta wave function. But this can be done. The first time, and actually the only time that I have seen it, is Slavnov gave lectures in Bezush. He has nice lecture notes, and he uses really more power, like more computations with ABCD operators and so on, to really show that the beta wave function is precisely up to some normalization factor. The coordinates,
It's horrible.
the entries of this. No, it's not so bad. No, I mean, so he really has like very slick notation. You know, it's very efficient, and then it's not so bad to do this computation actually. But this seems to be not so well known. So I was wondering about this long ago, and then finally Slavnov in his lectures showed this, but it doesn't seem to be so well known. But it's not so hard. I mean, it's a little bit more. It needs a little bit more kind of technology, like what we've been doing here, but it's not bad. So it can be done, luckily.
But if you ask people like Bajanov, or they will tell you that it's impossible.
Yeah, right. So, so I think this is what people used to think for long, but I think so. Slavnov's result, I think, is relatively recent, as far as I know.
Yeah.
So, yes, but this was the JS search. So when was this? In maybe 5 years ago. So that's the first time that I ever saw that actual proof. So that's the part that's usually missing, that you actually get the coordinate beta ansatz from this. But luckily, even that part is good. Okay, so this is the algebraic beta ansatz. Super easy. Okay, you have to do the proof by induction. So that's maybe the exercise. That's also an exercise. But if you know what to prove by induction, then the proofs by induction are not so hard, of course. And yeah, so now basically we finally recovered everything that we did in all the coordinate story, but now from this algebraic framework. So we know how to compute really to make the link from the transfer matrix to the Hamiltonians. We may know how to get the eigenvectors. We know how to get the beta equations and how to get their eigenvalues for the partition function. Right, please love that. So remember, now of course we have something like the Hamiltonian was something like logarithmic derivative at some suitable point of the transfer matrix, maybe plus some constant and maybe times some constant. So you see that the eigenvalue of the Hamiltonian will likely be obtained as the logarithmic derivative of our transfer matrix eigenvalue with the same constants. So that's how you also compute the corresponding eigenvalues, because you know everything in terms of the transfer matrix, so the same is true at the level of the eigenvalues. Now, of course, we get back to the discussion that we did a little bit at the start, is you have to show that the beta ansatz is complete and so on, but the beta equations are the same. So this is the same. This has been settled, but only rather recently. And it works well. There are some cases in which this genericity that I used to, for instance, here, so here we have an equation which is basically polynomial or trigonometric, like it doesn't have any denominators. Here I introduced lots of denominators, which may be bad if we are at some poles here. And for certain solutions, these poles occur. So this form of the beta equations are actually the better form of the beta equations. And there are other forms which are even better still. And those are the ones that are used to prove that their solutions correspond one-to-one to the eigenvectors of the transfer matrices. Okay, so now I want to talk about, so this algebraic framework, this quantum inverse scattering method with ABCD operators and so on, it gives us much more. So we cannot just reproduce the coordinate beta ansatz, but we can easily go beyond. And one variation which I think is nice to mention are called inhomogeneities. So remember that we have our Young-Baxter equation, this. So from the picture, it's actually, from the 6-vertex model point of view, all these lines, they're just lines of the lattice of the 6-vertex model. But the 6-vertex model doesn't particularly care that some of these lines are a bit more horizontal and some of them are a bit more vertical. So from the 6-vertex model point of view, it's very natural to also associate a parameter to this line here. So let's say x. And since we have our difference property for our matrices, we can do this by just simply shifting our u to be u minus x and our u prime to be u prime minus x. Then we still have that u double prime is u minus u prime. So we never changed this ratio. So we did not change the R matrix here, but we changed the arguments of this stuff here. Here we use, this uses the difference property, which we found. And I mentioned at the start of this lecture. And now graphically, as I already did, it's kind of quite natural to associate each of these different parameters to different local spaces. So what we're doing now is we attach u to our first auxiliary space, u prime to our second auxiliary space, like we did before, and now our new parameter v to our copy of C2, which maybe is the L side, like this. So maybe we should call it VL, if we will have more of them. Sorry, not VL, XL. Like this, and we might want to call it XL if we're going to do this with them. Graphically, what I'm now doing is the following. I'm saying that R of 0 L U minus now x or XL, let me just write x for now, corresponds to the crossing 0, u, L, x. And at this point, if you're fluent enough with these pictures and it's clear enough, you might want to, for instance, drop the labels 0 and L in the spaces and just for the lines, and just label the lines by their parameters. Because the parameters are attached to the spaces, so if you know where the parameters go, you know where the spaces go. So there's no point really in writing all of this stuff. So maybe you want to call this just like that. Now from this, we get a transfer matrix, which now depends on lots of inhomogeneity parameters. So u going through lots of x's like this, which if I write it out in a bit more details, u, I said 0, u, parameter, lots of vertical lines like this. This is 1, x1, dot, 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 l, xl. And with these horizontal boundary conditions, periodic boundary conditions. So this is a generalization of the transfer matrix. And basically, because everything is related by just this simple shift, everything that I've done works also in this case. Some of the results look slightly different, some of the formulas. So in particular, the eigenvalue of the A operator and the D operator is split into a product that depends, where each factor depends on one of these parameters. But otherwise, everything works really nicely. So what you can do, of course, is you can take a limit where you take all these XLs to go to 0. This is called the homogeneous limit. And then you recover our old friend, the normal transfer matrix, without homogeneity. And the reason why these parameters x are called inhomogeneities is the following exercise. So I claim that you can build a model, just a physical model, or a kind of a variant of a spin chain where you just have all these extra parameters sitting in there. So what would its conserved charges look like? Well, what we can do is we can take this transfer matrix and we can set one of its parameters equal to be one of those inhomogeneity parameters. So the exercise is to check that this equals hinge of eta times and then a big product of R matrices. So R, L, L minus 1, oh, x little l minus 1, dot 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 all the way down to RL1, x little l minus x1, and then back around R little l big L, x little l minus big L, dot 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 R little l l plus 1 with matching x's. Well, okay, that sounds so good. Let me write this last sentence. I was hoping it would fit. Finally, R L L plus 1, x L minus x 1, like that. All right, so first you're going to do this graphically. And find the relations that they obey. Or maybe first, rather, how does it compare with normal Heisenberg XXZ? So think about these operators and think how they compare to what we know about Heisenberg XXZ. Then in Heisenberg XXZ, the corresponding operators obey some relations. So what are the relations obeyed by these? So this exercise is a little bit more work. It really requires a little bit of thinking, but I think it's useful to, the first part is easy, and then the rest is useful to really think about what these inhomogeneities do for the model. Then from this, let me erase the algebraic beta ansatz. Another exercise is check that the R matrix, this is what I called R bar before. So R of u divided by A of u. So I choose my row so that the A coefficient, the 1, 1 entry is 1. Check that this expands as 1 plus eta times the little r of u plus order eta squared, where little r of u is 1 over the sinh of u times 4 by 4 matrix with 0 in the top left entry, then minus cosh of u, 1, 1 minus cosh of u, 0. So it looks a bit like what we had for xxz, but there it was minus delta, 1, 1 minus delta, and delta was cosh eta. Now instead we have cosh u. So it's sort of similar but different. This thing here, by the way, is called the classical R matrix. And it obeys a version of the Young-Baxter equation called the classical Young-Baxter equation, which you get by doing a similar expansion there. But for now, once we understand that this is true, then find the coefficients alpha j and beta j such that the following relation is true. So if you take 1 over sinh eta, then this transfer matrix that we computed in the previous exercise up there, xl semicolon x, normalized, but now we use R bar by some alpha subscript little l of x, is equal to 1 plus eta, and then some hl superscript g that depends on the x's, plus the beta of x times identity, plus order eta squared, where hl x with a g is minus the sum over all k which are not equal to L up to big L of this little classical R matrix R KL, acting at sides k and L, of xk minus xl And this is called the trigonometric Godin Hamiltonian. So this inhomogeneous XXZ spin chain contains, in some semi-classical limit here, by expanding in eta, this trigonometric Godin model. And this is interesting for many reasons. If you like geometry, that this is somehow, it has a duality which is related to geometric line lengths correspond. So this Godin, it shows up in a very kind of high-tech mathematics, but it also has nice physical properties. And to make the contact with usually people instead study, so let's take the residue at epsilon is 0 of this same Hamiltonian, where I multiply all the x's by epsilon. Then from this Hamiltonian here, you get the sum over k is not equal to L, and then you just get 1 minus phi kl divided by xk minus xl. But this is the rational Hamiltonian. By the way, if you want to do the kind of the hardcore version of this exercise, do it for x, y, z, and you'll get an elliptic Hamiltonian. But the same story will work. So here we have our 1 minus p, which was the local Hamiltonian of xxx, but now long range over all the k's which are different from L, so not just nearest neighbor, but any two sides interact. And there's some sort of potential, which is a 1 over the difference of these inhomogeneity parameters showing up there. I think I called it AL, BL. Right. Okay, and you can check, of course, that they commute for all the different values of L because of polars oriented to transfer features. So we find this and check that they commute. H Godin L, H Godin K, commute for all KL. At the same values of X. Okay, so that's sort of a little aside, but this is an application of using these inhomogeneities, and I think IPHT is a very suitable place to talk about the Godin model, of course, so I think it's good that at least I can connect these things here. Then one more exercise is, actually I could have stated it before, redo by great ansatz with inhomogeneities. So let's say for the inhomogeneous transfer matrix, or T of U with all the x's. And so in principle, you see that if you would really want to do this, you can also basically take the semi-classical limit. Things will sort of linearize, and you can do it even for Godin as an application. So this is an application of all these inhomogeneities. There's another application which I promised to do for part 1, but in terms of, for reasons of time, I wanted to do it following. So there's also application of all these inhomogeneities to combinatorics. So you can define, I'll leave some blank space on the left. You can define what is called the domain wall partition function. We briefly saw it when we were talking about different boundary conditions for the 6-vertex model. So graphically, and now I will introduce lots of parameters, so v and x. It's z subscript L, domain wall of all the v's and all the x's. And graphically, it looks like an L by L lattice, like this, with these domain wall boundary conditions that we saw before, which means that there are lots of thick lines coming in from the left and going out from the top, and dotted lines coming in from the bottom and going out from the right to the right. And then the inhomogeneities are sitting here, and there are also parameters v1 up to vl sitting there. So this is some partition function. It does not have periodic boundary conditions, but it has some certain choice of fixed boundary conditions. And the cool thing is that this one is not only exactly solvable, but actually explicitly solvable. So you can really write down a closed formula for this partition function. And I don't have enough time to do it. So the exercise is, there's an extremely nice paper about this, which was written by Greg Cooperberg. And it's on arXiv. Math/9712207. So what he did is, it was known, he realized that this thing, which is not only exact, but also explicit, which is different from the no beta ansatz equations. He realized that this thing, which was known from quantum integrability, can actually be used to solve by taking the homogeneous limit at the end of the day, so to send all the parameters to the same value, to solve a problem in combinatorics, namely the enumeration of alternating sign matrices. And alternating sign matrices have a nice history. They were, I think, I don't know if they were defined, but at least they were famously used by, what's his name, Lewis Carroll, the guy who wrote Alice in Wonderland. He was a mathematician. And for expanding determinants, alternating sign matrices show up. So it's kind of a good combinatorial thing to compute determinants. And so they're just simple matrices which have mostly zeros and then some ones and some minus ones. And the rule is that the ones and the minus ones, they should alternate occurring along the row. So there could be 0, 0, then a 1, then some zeros, then a -1, then some zeros. The next one has to be a 1, and so on. So in other words, the column sums, and you have to, and the rule is that you have to end at some point with a +1 and end with a +1. Okay, so that's and the same is true for all the columns. So in other words, there are matrices with entries 0, 1, and -1, whose row and column sums are +1. And they have to alternate the entries in between. And the nice thing is that you can enumerate them for a given L by L matrix exactly. And the proof of this, so this was conjectured long ago. And the proof, a very nice proof, uses this inhomogeneous domain wall partition function. And for the proof, the inhomogeneities are essential because you really use complex analysis of functions in multiple variables. So all the inhomogeneities are essential. Then you write down an exact and explicit formula as some Cauchy determinants times some other determinant, which was found by Izergian. And then you have to take the limit where all these parameters become equal, and you get enumeration of alternating sign matrices, as well as sort of refinements of this enumeration. So this is extremely nice. And if you're really interested in this, there's also a book by Britsu. So this is a very nice book in almost, he talks a lot about the history of alternating sign matrices, and he talks about Cooperberg's proof and all these things, but it's a whole book about this story. So it's extremely nice story. If I had maybe half an hour, I could do it, but I don't really want to do this now. So I'll leave it to the paper. This Cooperberg paper is short. It repeats kind of everything from my lectures that he needs. So he talks about the Young-Baxter equation, the solution of the Young-Baxter equation, all these kind of things. And then he computes exactly this partition function, following Korepin and Izergian, and then takes this limit to get alternating signs. So highly recommended read. So that would conclude part 1 of my lectures. What I want to do is kind of give a teaser about long-range spin chains, which are the thing that I like, which I personally work on. And I don't want to say too much about them, but I just want to show how they challenge our understanding of quantum integrability, to give you a bit of a better, because now maybe it sounds like a completely developed story where we can compute anything exactly, but there are a lot of things which are still open, and the long-range spin chains really give a good kind of some sort of idea of what is known and what is not known. But before that, maybe if there are any further questions about this, then we can do it. If not, then I should erase a little bit. We'll go to long range stuff. Okay. We won't need any of this anymore. Let me just keep this for now. So part 2, which is long range quantum integrability, and it's just a teaser, or it's called like a movie short. You know, like this is what you would see if you would really come back to the part 2 of the lectures. And I will just focus on the isotropic level for now. So delta is 1, x. The long-range spin chains, let's still consider the case where our Hilbert space H is C2 10 to the power L. We're back into the simpler world where we don't have any inhomogeneities, but just like this. And on this, we now consider a whole family of long-range Hamiltonians, which have pairwise form. So K minus L, well, minus the sum over K less than L, up to big L, then with some potential, V of K minus L, and then 1 minus permutation KL. So in fact, the Godin Hamiltonian is of this form. What I will want to do, unlike for Godin, is we'll assume that this is an even function. So V of, let's say, minus D is equal to V of D. And I will want it to be L periodic. So these are our periodic boundary conditions. V of D plus L is equal to V of D. Now, there are 3 spin chains which are relevant here, most relevant, and they have the following. So one we know, this is the Heisenberg XXX spin chain. So here, if I take my potential V of D to be 0 except when D modulo L is equal to L minus 1. Right? So we have smaller minus bigger. So if the difference of smaller minus bigger is equal to, well, minus 1, or L minus 1 modulo L, then it's correct. And because it's modulo L, well, actually, maybe you should extend this to be even, but it's not important. Here you see that it precisely picks out all the nearest neighbor terms, including the term 1, L. So this is okay. Then the next model is called the Inno spin chain. This one is more complicated. Its potential is essentially, up to some normalization constants and so on, the Weierstrass P function of D. Where the Weierstrass P function is a doubly periodic function, so it has periods L and something which we traditionally parameterize by I pi over kappa. And then the last one is following 3. And this has potential V is 1 over 4 sine squared pi over L times D. So this function is L periodic. Here we have an extra period kappa, well, parameterized by kappa. And we see that if we send the second period, so it's imaginary. So if we send the imaginary period to I infinity, which we can arrange by sending kappa to 0 from above, then this Weierstrass P function, if I give all the constants correctly, it will degenerate into this 1 over sine squared. And if I send kappa to infinity, then I send this imaginary period to 0. So this is kind of quite a brutal thing to do. But if you choose your normalization constants correctly, because we have kind of an infrared cutoff, because we have a spin chain length, so a minimum distance, even though this limit is highly divergent, we can make sure that it makes sense at the level of where D is an integer. D is 1, well, D integer, which is not 0, or not a multiple of L. And then you can check that it really becomes this Heisenberg potential. So the reason why I would like to, what I would like to say a little bit more about these models, and it won't take too long, is that so we have seen that this here is the paradigm for quantum integrable models. If you learn about quantum integrability, you will learn about the 6-vertex model or the spin chain, and we have seen that they're all closely related. So this is the standard integrability, which we've covered so far. This one here, it works very differently, but it is kind of a paradigm very well understood for long range quantum integrability. And this here is much less well understood. So this really challenges our understanding of long range, but actually more generally, quantum integrability. The physical interpretation is that we have this extra parameter. This is clearly the short range limit, so this is nearest neighbor. This here is intermediate range, where kappa controls the interaction range, and this here is really truly long range. This is just 1 over r squared. If you think of the circle, the spin chain circle, as sitting in the complex plane, in the unit circle. So if we think of this as the unit circle inside the complex plane, then this r here is just the chord distance between the particles. So you have these sides sitting on the circle, and they interact with a 1 over r distance squared potential, where the distance is the chord distance between A and L. So it has a nice geometric interpretation. Nowadays, people can build this in using these ion traps and cold atoms and so on. They can really put spins at very precise position, particles at very precise positions, and then let them interact with their spins. And they can really, we talked about this, they can kind of engineer one-dimensional systems, or in this case, they can, well, it would be really on a line, but then they can also engineer precisely the potential, and they can really arrange this 1 over r squared potential. So this is quite cool. And okay, so let me just summarize what is roughly known about these models. Very broad strokes. Okay, so we'll have 3 little headings. So first is the conserved charges. The second one is whether there's an underlying union in this case. And the third one is what the exact eigenvectors are. And for Heisenberg, we have seen that the conserved charges, they follow from the transfer matrix. The Youngian is given by this, is the Young-Baxter equation, algebra for the monodromy matrix with the rational R matrix. So clearly, from the monodromy matrix, we understood today how we can build this transfer matrix. And here we have the algebraic beta ansatz, which gives beta vectors, which today I denoted by this here. So this is the algebraic beta ansatz. And these are eigenvectors, exact eigenvectors, up to solving beta ansatz equations. So they're exactly parameterized by these parameters, which have to solve some equations, obey some equations, and often we will have to really construct vectors, we have to just solve numerically. So they're exact, but they're not explicit. On the other side, things work a bit different. So let me first go to Haldane-Schatzky. So here there are conserved charges. It can be done, but technically speaking, they come from the quantum determinants. Well, okay, let me write this down. So they exist. This was done by Talstra and Haldane, but they look different than here, and we don't use a transfer matrix. So not a transfer matrix. This here was a trace over 0. This is not a transfer matrix. There's also an action of the Youngian. So let me call it T tilde of 0. This exists, but it's different. So we still have an IPhT-TV operator, which obey the same Young-Baxter algebra relations of the Youngian, but the representation of IPhT-TV on our Hilbert space is different. And from this, if you like, kind of, it's not the trace, but this quantum determinant that I already mentioned. Let me take. And in particular, what this is some words, but what it means is that these charges, they are Youngian invariant. So Youngian symmetry. So this Haldane-Schatzky spin chain, if you take that Hamiltonian there with this potential here and you put it in the computer, you will see, and you numerically diagonalize it, you will see that the eigenvalues are, well, firstly, they are very simple. The numbers that actually occur are very simple. And secondly, they are very highly degenerate. So the same eigenvalue occurs many, many, many times, much more than you would expect, much more than for Heisenberg. And the reason is that the spin symmetry, the SL2 or the SU2, is enhanced to this whole Youngian. So A, B, C, and D all commute with this Hamiltonian print. So it's a very highly degenerate spectrum. It's a different representation on the same Hilbert space. And in this case, exact eigenvectors also exist. They exist, to be precise, for Youngian highest weight. But that's enough. So we have a symmetry, and if we can construct the highest weight one, then we can get everything else by acting with ABCD. And they are not only exact, but they're explicit. And they involve Jack polynomials. Special case of Jack polynomials. And this relies. So if you know about Jack polynomials, you know that they occur as eigenfunctions of the trigonometric of another integrable model of a very different type, which is called the trigonometric Calogero-Sutherland model. So this goes through a connection to this trigonometric Calogero-Sutherland system. And this trigonometric Calogero-Sutherland system is known to have Jack polynomials show up as its wave functions, and that's because the Haldane-Schatzky model is somehow related to this Calogero-Sutherland system. The eigenfunctions of Calogero-Sutherland show up in the eigenvectors of Haldane-Schatzky. There's a long story here which I'm completely suppressing, but this is schematically the picture. So if we compare, we see that it's rather different. So in both cases, we have an underlying Youngian. So I would say that both of these models are quantum integrable in the sense that there's an R matrix and blah, blah, blah. The representations, however, are different. In this case, we do what we've been discussing today and in the previous weeks. We make a transfer matrix, and now we can use the algebraic beta ansatz to diagonalize it. Here we do something else. We take another invariant, not a trace, but a quantum determinant. And it means that those operators are symmetric under the Youngian. So ABCD commute with all the charges, including this Hamiltonian that I wrote down there. The translation operator is also one of them, by the way. Since ABCD commute with them, we cannot use the algebraic beta ansatz, because if we act by the B operator, we will never change the eigenvalue, because they commute. So the construction for eigenvectors is rather different. And this can still be done, but there's really some sort of underlying technology in here. So let me write a sort of, it can be done, but really there's a lot of extra stuff hidden in here, which is how we actually get these exact Youngian highest weight eigenvectors. So why does the Ina-Zemtsev spin chain finally challenge our understanding of long-range quantum integrability? Well, so let me start at the bottom, which is the thing you do first. So here you can do a version of what is called the extended coordinate beta ansatz. And this extended coordinate beta ansatz eventually gives you a connection to the elliptic Calogero-Sutherland system, which is much more complicated than the trigonometric one. They're not nice, simple Jack eigenfunctions. And eventually, you will have to solve beta ansatz equations. That's kind of good in the sense that InnoZemsev interpolates between Heisenberg and this Haldane-Shastri, and it has features of both. On the one hand, you can do a beta ansatz type thing. On the other hand, it gives a connection to some Calogero-Sutherland type system, but then it's not explicit, it's only up to solving some very complicated beta equations that this works. So in my language, this is exactly solvable. It's complicated, but there is an exact description of the eigenvectors. In this case, the beta ansatz equations are much more complicated. There's not really a proof of completeness beyond 2 downspins. And even numerically solving them is much harder, but in principle it can be. So it's exactly solvable. Again, energy is, well, it's not quite. Remember, for Heisenberg, we had these additive energies, which gave us the quasi-particle picture. So for InnoZemsev, that's not quite true, but still the energy has a nice enough result that you would expect the model to be integrable. If it's exactly solvable and the kind of physical quantities have nice enough properties, then you would hope that there are also underlying conserved charges that commute with each other and sort of guarantee that this happens. And so in this case, there's a proposal and a partial proof. This is due to InnoZemsev and then Dietrich and InnoZemsev. But basically, there's a whole family of operators which have been written down, and only for the first 2 in the family, including the Hamiltonian, it has been proven that they really commute. So it's a very minimal version of conserved charges. But currently, with my collaborators, we're making a lot of progress here. So basically, this part is settled. Kind of, that's what we're working on now. And this Yangian is completely unknown. That's the reason why this InnoZemsev spin chain is so much harder. So in my definition, this model is not yet quantum integrable. We don't know yet if there's really an underlying Yangian or some sort of nice quantum algebraic structure, R matrices, and so on, that really guarantee all of this stuff to be true. And this is just for a spin 1/2 model with L sites. So it's isotropic. So it's a very basic type model. Physically, InnoZemsev is interesting because it allows you, if you really understand InnoZemsev, then you can really see how properties that we understand very well from short-range integrable models to properties that we understand of long-range integrable models, how they change as you really go from one to the other. And you can really study what the influence of long-range interactions on the model is in a setting which in principle is at least exactly solvable. But the tools are currently kind of lacking to really do this, to really extract things that kind of could be matched with experiments or really give more physical insight. So that's what we're working on. And for instance, if you have these neutron scattering experiments that I mentioned at the start, which is where Heisenberg really occurs in nature, InnoZemsev, so you might imagine that these spin interactions, they are not quite short range. So short range is a very good approximation, but there might be some influence of beyond nearest neighbor interactions. And InnoZemsev would give an exactly solvable setting in which you could kind of study that kind of very close to Heisenberg, but slightly different. So I think there are a lot of good motivations to study it. Also, from a theoretical point of view, we're really challenging what we understand about exact solvability, integrability, and so on. And so that's kind of the work that we're doing with my collaborators. And that's what I wanted to end with. So thanks.
Yeah, basic question. So what do you mean exactly by exact solvability? Because
right.
You define the Hamiltonian, so you can, by definition, you can always diagonalize it. What does it mean?
So here I
would give an example maybe of a non-exactly solvable.
So by exact solvability here, I mean, well, so more precisely, I mean this beta ansatz solvable. So there is a parameterization of hopefully all eigenvectors, modulo issues of completeness which are not completely settled. So hopefully there's a parameter, or there's this parameterization, and it is of eigenvectors up to solutions of these beta ansatz equations. And maybe you remember that for the Heisenberg model, I told you that the beta ansatz equations, they are nice in the sense that, for instance, we can characterize by specifying integers what the antiferromagnetic ground state is, what maybe the lowest excitations around it is. So it's a really a physically meaningful parameterization. And by solving the equations eventually maybe numerically, or studying what happens with certain classes of physically most important solutions as the length increases, you really get a good, extremely good control here over the model. So here, in principle, everything is in place to do similar things. The details are much harder, but that is what we had. That's the type of exact solution that does exist. So for instance, you can exactly describe what should be the antiferromagnetic ground state. Solving the corresponding beta equations in this case will already be harder, but I think I can characterize which solutions one should look at. And for instance, it's good enough. So with a collaborator, I studied with Rob Klappers. We studied the passage from Heisenberg all the way to Haldane-Shastri for the sector with 2 downspins, which is the first case in which you really start seeing interactions. And there we can take these the coordinate beta ansatz wave functions here, show that this here really limits to those there and limits to the known eigenvectors with Jack polynomials there. And we can really study what happens with solutions of the beta equations from here all the way through long-range interactions to the point that you get to this Haldane-Shastri. And we can really study how the quasi-momenta, how they behave. Sometimes they in the complex plane. So you have 2 quasi-momenta, and what can happen is that they can bounce off each other essentially. So they can kind of collide in the complex plane, and we can really characterize for which value of the parameter kappa this happens, and so on. So we have a lot of control over this for 2 downspins. But from 3 downspins onwards, it starts to get much harder. And the hope is that by developing this general picture, we will also have better tools to study that. So I don't want to give you a precise answer because, you know, I want to give an answer which is vague enough that it fits everything that I want to fit. But certainly these models, they fit in my vague idea of what exact solvability.
If I pick a random function v, periodic and even,
Well, must be exactly solved. Yeah. So so almost never will such a model have a beta ansatz type solution which gives some physical intuition and control over what the eigenvectors look like as you vary the length or as you vary the parameters. Of course, you can numerically do it, but it will not give you too much. Here we really have exact, even though not explicit, control over what happens.
so is the Weierstrass function the most general one, which
Right. So this fits in a sort of yes. So in this class of models, it's basically because these Calogero settlement type systems, they occur in elliptic. And then it has a trigonometric and a rational degeneration, and actually there's also a hyperbolic degeneration, which is as you send the length to infinity. And that's what's underlying these type of models. This hyperbolic case is here too. If you send the length to infinity, so you make a longer and longer and longer chain, then this Weierstrass P becomes a 1/sinh of kappa squared, kappa d. And that's still beta ansatz solvable. In this case, the beta equations are simpler, and it would be related. The eigenvectors are related to those of the hyperbolic Calogero system, which again are much easier to understand. So that would be relevant for really microscopically big one-dimensional systems with these type of interactions. So those do fit because there's this kind of standard, I guess, families of functions that are nice. But beyond this, well, there's some other variations. So you can add a confining potential. So you can add a kind of a v squared type of potential. Then somehow what it means is that these particles, these sites, they have to move a little bit, and then they're at zeros of Hermite or Laguerre polynomials, blah blah blah, and then those models actually also fall in this long-range type of Haldane-Shastri that we have here, where there's some sort of Yangian symmetry and all this kind of stuff. So there are variations, but it's very delicate. So the long-range integrable picture is very delicate, and usually you're very far away from it.
You say you don't know the conserved quantity.
Right.
Maybe I misunderstood. You
So
say
this is well. So there's a conjecture for conserved quantities, there's a proof, an explicit proof that the first two of this family actually commute. So this is the status from the mid-90s onwards, and it's basically not been touched.
You mean the first to the momentum and the Hamiltonian?
No. The Hamiltonian and the first one goes beyond. Of course, the translation is already in there. So one beyond the Hamiltonian. But with this collaborator, we now found. So basically, what we did is this was only a delta as 1, but we now constructed a version for general delta of the Innocent spin chain. It's much more complicated, but here we can really derive explicit Hamiltonians and show that they commute. Like what we did for Q deformed Haldane-Shastri over here. So we can do the same at this column. So in fact, it implies that there will be many commuting Hamiltonians here. But the problem is that this limit delta going to 1, all of our higher Hamiltonians, they all become the same, like for Q Haldane-Shastri. So you have to take a non-trivial, you have to kind of study the difference in this limit. So getting explicit Hamiltonians is work that we haven't done yet. But in principle, we have sort of an indirect proof of this commutativity after like 30 years of this being open. So it's a hard problem, and we're making some progress. But
just to mention the simpler, I mean, if you have the Taylor-Sutherland model with 1/c² potential, I don't think the wave functions are known.
Well, they're sort of known. So there's a construction by Chalet and Vizilov, which give a recursive description of these wave functions. So they're quite easy. You take some function and you act on it by derivatives, a bit like what you do for Hermite polygons. So this has been done. So hyperbolic, there's a very good control over wave functions, at least for some range of the coupling. But the elliptic is much harder. Of course, there's work by Felder and Varchenko and others. But it becomes much less explicit. I mean, it becomes much more implicit. It was already not explicit, but now it becomes extremely implicit. But we think that it's still good enough to understand things exactly that are physical relatives. Any other questions? Not? Then precisely at 1/2 past, let's finish.